Good morning, good afternoon, good evening, class. This is Mr. Arosena, and today I'm going to be talking about organic chemistry. Well, it's basically a brief introduction to organic chemistry. Organic chemistry is a very broad, very big topic, and we kind of don't spend enough time on it, but that's okay. If you guys continue on in chemistry, you'll definitely see more of this. So today will just be a short introduction to what organic chemistry is, and a few things regarding naming. Alright, so what is organic chemistry? Chemistry we can break down into, I guess, two different types. Inorganic chemistry and organic chemistry. And the basic definition is that inorganic chemistry is chemistry regarding compounds from mineral sources. So things like it came from a rock, basically, or it came from a mountain, or it came from the earth, or something like that. Organic chemistry is basically a study of compounds from living sources. So if a living thing made it, we can consider it organic chemistry. Okay? If a non-living thing made it, it's basically inorganic chemistry. Alright, now what propelled people into studying organic chemistry, and what actually really opened up the subject, was the creation of urea. So urea is a compound found in your urine, and one of the greatest discoveries was that this chemist named Wöhler was actually able to synthesize or create urea in the lab without the need of an actual person to pee it out. Okay, because before then, people thought that organic compounds needed something called a vital force. So let me underline that. Okay, this vital force. This thing was apparently what was needed to create all organic compounds. Because, again, organic compounds came from living things, so it made sense that living things had something within them that was required for creating organic compounds, which at the time chemists called a vital force. Now when Wöhler synthesized urea using, this is important, inorganic compounds, he used inorganic compounds, he was able to create urea. Okay. I imagine that at the time, a lot of chemists thought that this vital force was necessary to create organic compounds, and then Wöhler comes along and all of a sudden, hey look, I made urea and I didn't have to use living things to do it. So it was really cool. Just basically, Wöhler showed that organic compounds did not require this vital force that a lot of other chemists thought. That if you had the right processes, you can create organic compounds in the laboratory. All you needed was the right compounds and the right processes. It really propelled people into looking for cool things and what they could do with organic chemistry. It has led to some pretty interesting discoveries. For example, like you can make sugar, you can make penicillin, you can make a lot of organic compounds without actually having to go through the whole process of having a living being created for you. Okay. Now, the majority of organic chemistry is really the study of molecular carbon compounds. Okay, now, one thing to note is that this is molecular carbon compounds, or basically covalent carbon compounds, not ionic. Okay, because ionic carbon compounds are things like any kind of carbonate compound, or things like that. They're basically minerals. Okay, so organic chemistry is not the study of minerals. Organic chemistry is the study of other carbon compounds. Now what's neat about carbon is that in the grand scheme of things in the universe, there are several million carbon compounds. And because carbon is just a very interesting element, it can combine in so many different ways that there are millions of carbon compounds. Contrast that with, at the time of creating this presentation, only a few 100,000 non-carbon compounds. So carbon is very popular, and it's created many things. Okay. And organic chemistry is basically the study of carbon compounds. Although, again, not ionic carbon compounds, but molecular carbon compounds. And if you remember from earlier in this semester, molecular is really just another name for covalent. Now what makes carbon really special? Well, The majority of it is this. The carbon can form up to 4 bonds, and it can form them in combinations of single, double, or triple bonds. We already discussed double and triple bonds earlier when we were talking about covalent bonding. Okay, we'll discuss, and the double and triple bonds play a little bit more of a role in organic chemistry. Now, what's cool about carbon is that these bonds can then bond together to form chains, rings, spheres, and tubes. So all of these, every single one of these pictures is a different type of carbon compound. So this is a chain of carbons. So that's a chain. This is a ring. That's a ring of carbons. These are sheets of carbon. This is a sphere, sometimes known as a buckyball. Spheres of carbons, and these are tubes. Okay. So these are all the different types of shapes that carbon compounds can make. And each of those shapes has a different property. Okay. For example, sheets are very, very conductive forms of carbon compounds, whereas spheres are not really. The carbon tubes are very, very strong, but a single carbon chain is not very strong. Okay? So these are just some cool things that carbon can do, and because of it, carbon is a very, very special element. Now, as I mentioned, the arrangement of atoms does change the compound's properties, even if the compound has the exact same chemical formula. So let's look at, as an example here, there's 4, so each of these is a carbon, so that's a carbon, each of these is a hydrogen. And when you look at the two compounds, they have the exact same number of carbons, exact same number of hydrogens, but because they're shaped differently, the two compounds actually exhibit slightly different behaviors. Okay. One of the compounds is more flammable than the other compound, or at least it requires less energy to ignite. Okay. And all of that is simply because of how they are shaped together. Okay. So that's what's really cool about carbon, is that how it's shaped, how it's combined, what it's combined with, all determine what kind of chemical properties that particular compound has. Now, in the context of organic chemistry, most of the simple organic chemistry deals with compounds which are called hydrocarbons. Now, hydrocarbons are compounds consisting of, as the name suggests, just carbon and hydrogen. No other element, just carbon and hydrogen. Okay. So that's why we call them hydrocarbons, because again, only consist of hydrogen and carbon. Okay. Now, what's neat about hydrocarbons is that they tend to form very long chains. Okay, so they form long chains, and sometimes the chains can branch. And if it does branch, we look for the longest chain, which we call this the carbon backbone. And as far as naming compounds go, identifying the carbon backbone is the most important part. And then we can identify the branches later. So hydrocarbons tend to form long chains of carbons and hydrogens. Okay. Now these chains can come in two varieties. If we can consider saturated hydrocarbon chains and unsaturated hydrocarbon chains. And the only difference is basically how many hydrogens are there. Okay. So a saturated hydrocarbon will have the maximum amount of hydrogen atoms bonded to the carbon. So maximum amount of hydrogen atoms bonded to carbon. So an example, this here, this is saturated. Okay. And we can tell it's saturated because every single carbon is attached to something different. Okay, it's either attached to another carbon or it's attached to a hydrogen. Okay, there are no double bonds between them. There are no free bonds. Okay. This one over here on the right, this one is unsaturated. Okay, because while the majority of the carbon, oh sorry, not the majority, this carbon here in the center is attached to 4 different things. This carbon here is not, because it's got these 2 double bonds to this carbon. So these 2 carbons, I'll highlight them here, have the potential to attach to other things. Potential to attach to other things. And that's what makes that unsaturated, because of that potential. You can either attach to more hydrogens, so if the 2 carbons in the middle, so again this one and this one, they can choose, or if the situation is right, they can attach to other hydrogens and then they can become saturated, or they can attach to other carbons and extend the chain, or they can attach to other elements and become saturated that way. Okay, that's basically the difference between a saturated hydrocarbon and an unsaturated hydrocarbon, is basically how many or does it have are the carbons all attached to something different, or are there double bonds or triple bonds? If it has a double bond or a triple bond, it's unsaturated. If everything is single bonds, then it is saturated. Okay, used to be a very big thing in diets probably a decade ago now that I think about it, where there's a big push for unsaturated fats and saturated fats, because saturated fats were bad for you, and so on. Okay. So in diet, this is still a big thing, because fats are really just long hydrocarbon chains. But we'll discuss that later. Right, now there are a number of ways to sort of draw carbon compounds. We've already discussed dot diagrams. These are really no different than what we did previously. So for example, let's use my example, let's use an example of, we'll just do a simple 2 carbon chain. C2H6. Okay, so the dot diagram for this would look, for C2H6 would be like this. C dot dot H dot dot H dot dot H dot dot C dot dot H dot dot H dot dot H. Yeah, so this is the dot diagram. Good for small carbon compounds, but when you get larger carbon compounds, it tends to be very, very clumsy. A complete structure is kind of like the dot diagram, but rather than drawing dots, we just draw straight lines to show the bonds. And then each straight line is understood to be a pair of electrons. Okay. Condensed structure is very, very similar. The only difference, let's use green, I guess. A condensed structure basically condenses the hydrogens, so you would get CH3 connected to CH3 like that. And it's understood that the H's here, so these H's are connected to that carbon, these H's are connected to that carbon. So that's kind of what the condensed structure is. And the line structure, there's actually 2 ways you can draw the line structure. The line structure is even different still. A line structure would look like this, C2C. That's one way of writing the line structure. We don't write the hydrogens. It's assumed that all empty spaces, or all empty, it's assumed all the empty carbon bonds are taken up by hydrogens. Okay, for longer chains, like for example, if I had a for longer chains, sometimes it's handy to just ignore the C's, so you just end up getting a straight line like that for this one. If I were to do a 3 carbon chain, so C, 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 a 3 carbon chain would look like this. It's understood that each point has a C. 4 carbon chain, let's see, 4 carbon chain, if I had 4 carbons together, would look like this. Again, understood that each point has a C in it. Okay. So for short carbon structures or short carbon compounds, dot diagrams, complete structure, and condensed structure will work just fine. But if you're getting into really large carbon chains, like for example, as we start getting to, let's say, 8 or 10 carbons, sometimes it's easier to just draw a line structure. And to be honest, this is my preferred method of drawing organic carbon compounds, so I'll probably just draw that from now on. Alright, so there are ways we can represent the carbon compounds. Now, how do I name them? So, more naming. Carbon compounds are named, or at least hydrocarbons, have a very specific naming convention. Sort of like any other chemical naming convention. In some ways, though, I think naming hydrocarbons is easier. Now, there are two things to note. The first is that the name depends on the number of carbons and which family of carbon compounds. And we'll discuss what family of carbon compounds means. So the very first one, and very simplest, we call them alkanes. Okay, alkanes are the simplest and they are the easiest to name. The reason why they're the simplest is because of this. No double or triple bonds. So no double, no triple bonds. So it's basically carbons single bonded to carbons and every other bonding space taken up by hydrogens. Okay. So that is what an alkane is. Now to name an alkane is fairly easy. Okay. So let's start with straight chain. Okay, a straight chain alkane is basically a hydrocarbon chain where the carbons are linked to other carbons in one long chain. And every other valence electron is bonded to a hydrogen. So all the empty spaces are bonded to hydrogens. And the naming depends on, again, how many carbons are in the chain. So for 2 carbons is ethane, ethane for 2 carbons, propane for 3 carbons, bute for 4. I'm not entirely sure, I forget the reason why it's eth, prop, and bute for 2, 3, and 4. For 5, and now it starts to make more sense, 5 is pentane. Pentane is 5 carbons. Okay. 6 is hexane. Hexane for 6 carbons. 7 is heptane. Hept was 7 in Latin, I think. And so on. 8 would be octane. 9 carbons would be nonane. 10 would be decane. And so on. And then page 695 in your textbook lists them all. So you can just look in there. So if it's just a one long straight chain of carbons and all the valence electrons are bonded to hydrogens, then we just call them alkanes. Okay. And then we name them ethane, propane, butane, pentane, hexane, and heptane. Okay. Oh, and your textbook mentions this, but I don't have it in my notes, but I'll do it anyways. So 1 carbon, we call this methane. Okay. So, eth for 2, prop for 3, bute for 4, and then pentane, hexane, heptane, octane, and so on. And then meth is 1 carbon. Okay. There we go. So that's a straight chain alkane. Now, what happens if they branch? If an alkane branches, well, a good example of this would be if, let's say I had a 1, 2, 3, 4, 5. Yep. And let's say I branched off this carbon into another carbon another carbon like that. So that would be considered a branch, because we have this this portion here is a branch. Okay. So when you have a branch like that, we name it as follows. First count what is the largest chain of carbons. In this case, the largest chain of carbons would be 1, 2, 3, 4, 5. Would be like that. Okay, there's a chain going 1, 2, 3, and then you could choose 4 there, but that's only a 4 chain, it's not the longest. So the parent chain is the longest chain of carbons, so that's what we would call. We would start that way. Okay. And we would call that, that's where we would sort of start there. So in this case, the longest chain of carbons is 5, so this is some kind of pentane. Okay, pentane. Okay. So we'll start there. We'll start by calling this a pentane. Now, we just have to decide, what do we do with that branch? How do we name the branch? Well, each branch is what we call a substituent. Branches off of the parent chain. So here we have a single carbon branching off of the 3. So that chain is a chain of 1 carbon. So 1 carbon chain. So this branch, 1 carbon. We would start off, well, 1 carbon is usually called a methane. But because it is a chain, or because it is branched off of the parent chain, rather than calling it methane, we'll change the ending to -il, so it becomes methyl. So this is a methylpentane. But wait, does the location of the branch matter? Yes, it does. Since the methyl branch is on the 3 carbon, we'll call this 3-methylpentane. So this tells a chemist that at the 3 carbon, so at the 3 carbon, oops, okay, cancel, at the 3 carbon, there is a methyl group. That's what that means. Methyl group. Oops. Okay. That's what 3-methylpentane means. That there is a methyl group at the 3 carbon. Okay. Let's go through some more examples of this. Okay. Alright, let's go through some more examples. So let's say I have a carbon chain. 1, 2, 3, 4. 1, 2, 3. So that's a 6 carbon, whoops. So this is a 6 carbon chain. So this is going to start, whoops. This is going to start as a hexane. There's a hexane. Okay, I should actually not have put it there. I'm going to branch this off actually. Let's make a branch here. 1, 2. So here I have a 2 carbon branch. Right. So let's look for the longest chain. So 1, 2, 3, 4, 5, 6. There you go. We could also count it 1, 2, then 3, 4, 5, 6. Regardless, the longest branch is 6 carbons. So 6 carbons, longest branch, 6 carbons. So we're going to start off, this is going to be a hexane of some sort. Okay, next. Let's identify the branch. Well, the branch, let's say this is my branch. Okay, my branch consists of 2 carbons. So a 2 carbon branch. Okay. Normally 2 carbon chains are called ethanes, but because this is a branch, we will still use eth, but instead of ethane, we'll call it ethyl. Okay. Now, where does this? And the last thing we need to do is identify where this branch comes, or where this branch is located on the main parent chain of the hexane. It's located on carbon 1, 2, 1, 2, so 3. So this is 3-ethyl hexane. Okay, that's how we named the branch. All right, now, what if we have multiple branches. We have multiple branches. If we have multiple branches, we'd end up naming them exactly the same. Oops. One. Or that's not exactly the same. What am I talking about? We'd name them, let's say, well, let me just draw a branch. So let's draw a branch of, let's say, so another hexane. So C, 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 C. So there's a hexane. And let's say I have a branch there and a branch there. Okay, so I already said this is a hexane. Hexane. Okay. Now, I've got two branches this time. I have a branch of one there and a branch of one there. So I have two 1-carbon branches. Okay. What does this mean? Well, a 1-carbon branch we already identified is called a methyl. So I'll say methyl here. But because I've got two of them, I'll call it dimethyl. Okay, so I have two methyl branches. I'll call it dimethyl. Now, where are they located? Well, let's number these carbons. 1, 2, 3, 4, 5, 6. So this is actually, the two methyls are located at 3 and 4. So this is 3,4 dimethyl hexane. Basically, it says that at the 3 and 4 carbon, I've got a methyl on each of them. And that's how you would name it. Right. That's basically how you name a branch chain alkane. Now, what about, and it's going to look really strange, what if I have different types of branches? Okay, let's use hexane again, because hexane is, let's say, another hexane chain. So let's say I have a 2-carbon chain there and a 1-carbon chain there. Well, this is a hexane. We'll identify this as a hexane. Hexane. And then I've got an ethyl branch here. So this is an ethyl branch. This one here is a methyl. And this is how I would number it. Carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. So, I would say the following. At the 3 carbon, I have an ethyl. And then at the 4 carbon, I have a methyl. There you go. So this would be 3 ethyl, 4 methyl, hexane. Okay. And that's how you would, if you have different branches, that's how you would name them. You just identify what is each branch, where is each branch, and then you just stick it in front of whatever your parent chain happens to be. Okay? Alright. Let's continue. But there you go. That's how you would name a branch chain alkane. Right. That, you guys should be able to complete your assignment. If you guys have any questions, you guys know how to contact me.